Yes, it's
Sir, just
visible, sir.
wanted to, yes, sir, it's visible. Just wanted to introduce you, sir. So today now we have talk 2 of our last day by Professor Jitendra Sangwai. Dr. Jitendra Sangwai is currently working as professor in the Department of Chemical Engineering at Indian Institute of Technology, Madras. He obtained MTech in 2001 and PhD degree in 2007 in chemical engineering from IIT Kharagpur and IIT Kanpur, respectively. He has worked with Schlumberger dealing with flow assurance issues and on several commercial projects. As of 2022, he is having more than 18 years of professional experience. Sir has published several papers in international journals and conferences of international repute and has won the highly cited author award from the Industrial and Engineering Chemistry Research ACS Journal 2020. Sir has filed 15 patents in the field of gas hydrate, enhanced oil recovery and flow assurance. Professor Jitendra Sangwai is recipient of National Geoscience Award from the Government of India 2019 for outstanding contributions in oil, natural gas and gas hydrates. Professor was also awarded the National Award for Technology Innovation from the Government of India in 2016 and 2018. Dr. Sangwai also has been elected as Fellow, Indian National Academy of Engineering 2024. Sir, we welcome you for the session. Sangwai, sir. Yeah, sir, you can continue. Yeah.
Sorry. Yeah, am I audible now?
Yes, sir. Audible.
Yes, sir, you are audible.
Yeah. Okay, sorry. So I'll keep my video off. I think it's not
Okay.
required, right?
Yes, sir. No problem.
Right? No problem. Yeah. Anyway, so thank you so much for introduction and inviting me for this workshop. So today I have made my presentation in two parts. First, I will talk about, so the focus is primarily on to the sequestration overall, but before I tell you about the sequestration and before you understand what is the sequestration that I am going to do, you also have to understand the capture process. What is the capture and what is overall goal of CCUS, strategy. So the first part I will briefly discuss about on the carbon capture aspects, and then the second part I will discuss about sequestration into the ocean. Now, okay, let me see. Okay. So I will not go in detail about that, but my introduction is, I think Della had already given that, so I will skip that. Various activities have been carried out in our lab since past 15 years on various aspects of oil and gas industry. Specifically on the upstream side, we have been working on gas hydrate as issues in oil and gas industry. Primarily, you talk about flow assurance in the pipeline. We have also worked on issues like wax deposition in the pipeline, asphaltene deposition in the pipeline. So one of our goal was also to recover oil from the subsurface reservoir using enhanced oil recovery method. So we have been working on use of nanoparticles or nanofluids for injection into the reservoir, and so that we can recover more oil. We have also been looking at CO2 injection into the reservoir, where CO2 can be utilized from the power plant, so that we can also recover oil from the reservoir and also sequester most of the CO2 into the subsurface reservoir. In addition to that, we have also been looking at currently on the carbon sequestration into the ocean in the form of gas hydrates, on which I will discuss that in a detail. I will also show you that how the gas hydrate are one of the potential source of energy for the mankind in near future. And in addition to that, we have been working on reservoir engineering aspects. We have been working on drilling fluids or fracturing fluids. And that way, many of our PhD scholars have carried out variety of work in the various domains. So today's talk, I will focus on primarily on carbon capture and sequestration. So we know that carbon dioxide has been emitted for now several decades, and in order to ensure that our environment temperature or atmospheric temperature remains within 1.5 or 2 degrees centigrade, we require to have immediate steps to be taken. And I'm not really going in too much of data over here, but I'm sure that this has already been discussed in some of the other discussion. But every year, we have been emitting about 33 to 34 gigatons of CO2. You know, and it has now increased to 36, 37, and you can see this plot that it shows that it's continuously rising, and that is resulting in the atmospheric CO2 concentration in somewhere about 280 ppm in 1750 to more than 400 ppm. It's close to now 420, 25 ppm. So one can see that the concentration of CO2 is rising, and therefore it has been providing significant impact on the environment, and therefore it is important, in addition to address various other pollutions, it is also important to curtail the CO2 into the environment. However, there are various challenges associated. In order to curtail that, we have to also go on renewables, significantly using solar. You can have biomass based sources. Biomass is also not a carbon neutral, because ultimately when you use biomass, you are going to emit carbon dioxide into the environment. So therefore, there has been critics on biomass uses as a energy source. Even though people say that it is a carbon neutral, specifically nature captures carbon dioxide into the biomass, and if you really want to burn that, you are actually releasing that CO2 into the environment. So therefore, we required immediate steps to capture carbon dioxide from the environment and sequester that, right? You can convert CO2 into the value-added products. That's one pathway. But again, that is very energy intensive pathway, because you require energy to even convert CO2 into any value-added product. And therefore, even if you are going to utilize carbon dioxide, say, to generate a methanol, you are going to emit a lot of CO2 by actually converting CO2 into some product, right? So as of now, it's far away, to look at conversion of CO2 into any value-added product, because of some of the constraints that provides in conversion of CO2 into some of these products. So if we understand the pollution, one can say that pollution can primarily into the solid, which is a land base. We can see that the plastics are lying everywhere, plastic pollution and many other stuffs. Reasonably, the molecules are very closed here. These are in solid form, and therefore it is relatively easy to segregate this pollution. Of course, one of the challenging factor over here is that you have to degrade that. All right. So therefore, you need more sophisticated methods to degrade these plastics in a short time, so that you can address the environmental concern. However, capture of such plastics is relatively easy. I'm not talking about the post processing of this solid waste management, but even you want to segregate that, it's relatively easy, because you can do that even through the manual intervention. When you have liquid water, which is getting polluted by means of dyes, here the molecules are in a liquid form, and therefore it's relatively very challenging to separate this pollution from water stream, and then address that pollution as compared to solid, right? However, it is reasonably easy than the pollution that we put it into the air atmosphere, because here the molecules are getting segregated into the atmosphere. They are dispersed into the atmosphere, so the molecules are very difficult to capture. Your atmosphere is a very large. In all these previous cases where you have solid waste management, you have water pollution treatment plant, etc., your molecules are more confined in a specific area, specific zone, and therefore, within the purview of your manual intervention, you should be addressed to partly address this pollution, which may happen in a land-based condition or even in water-based bodies. However, when you pollute something into the atmosphere, it's gone into the air, and it's very difficult to capture that, right? And therefore, the pollution, once it is gone into the atmosphere, it's very challenging to address. So therefore, one has to understand that how I should reduce this pollution into the environment, and that should be the first primary goal. Now, currently, most of this energy that we consume is primarily related to the energy. I mean, the most of these the CO2 emissions that are responsibly into the environment is primarily because of the energy factor. We also have the agriculture, waste, and industry, but one can say that 73% of emissions into the environment is primarily because of the energy uses, and the energy can be utilized in various industrial activities. It can be utilized in transportation, in buildings, in other combustion activities, etc. So, and when you talk about energy, it's very important to survive, specifically when you look at the growing population across the world, right? So population is continuously increasing, whether it is our country, China, or world population that you talk about. The increase in population also demands more energy for survival, right? Now, therefore, when we talk about the consumption of energy, it's very directly related to the amount of CO2 that we release into the atmosphere. Now, you know that we are now close to $3 trillion economy, I mean, we are more than $3 trillion economy. We plan to go for 5 and then 10 and 15 and 20, right? So we are looking for increasing our economy. We are looking for increasing our GDP. And when we try to understand the economics of overall country that we plan to increase the economy, it cannot come without emitting carbon dioxide, because economy is directly proportional to the consumption of materials or anything that we have in the market, right? The more you consume, the economy will grow. Today we will stop buying everything from the market, whether it is clothes, whether it is laptop, whether it is anything that you consume, in including foods, pizzas, and their packings, everything. You have plastics, you have car, you have petrol. So anything that we consume will directly affect your economy. So if you stop buying anything, then your economy will not grow. And therefore, once we become more consuming nation, uh, it requires energy, because anything, it's not a magic that everything is available, just a pinch of salt. You have to have industries to manufacture that. For example, if you look at the number of automobiles that have increased in last 10 to 15 years, you will see that number of automobiles in each household has increased drastically, even including cars or two-wheelers. Nowadays, we do not even see cycles on the road, because primarily everybody is now wants to have more luxurious life, comfortable life, by using two-wheelers or bicycles, gone away from the roads. We want more air conditioned units in classrooms everywhere. So energy usage is day by day increasing. And the more you become habituated, you have to have energy that can support your lifestyle. However, when you talk about this energy and its direct impact on the global temperature, or the CO2 emission, one can see that the global land to ocean temperature anomaly has increased somewhere about 1970s onwards. And it has increased so that the land temperature is continuously rising as compared to ocean temperature. And that's because you have more CO2 into the environment, more pollution, you have more cement that is happening, concrete jungles are there are hotspots available in the overall land-based scenario. And therefore, in order to curtail that temperature, increase in temperature, you may have three major scenarios: scenario A, B, C, that I have shown here, where if you do not curtail, it's end up going significantly high beyond even 1.5 degrees centigrade in short period. And if you look at scenario C, where you can actually try to curtail your emissions, then you can reasonably understand that you should be able to, control the temperature within 1 degree centigrade rise in near future. However, if you look at the lesson from the coal, everybody knows that coal was primarily used early days in transportation, primarily running our trains, right? And then the usage of coal has stopped somewhere in 1950 onwards, or 60, somewhere in middle of that, just because of the pollution. Because it has been observed that the trains which were running on coal-based turbines, they are actually polluting a lot of environment, and therefore they stopped it. And then most of our trains have been converted into electricity-based mechanism, where you have electric lines, and then you can actually have your transportation by trains, or all kind of vehicles on the tracks goes on using electricity. If you look at the use of coal into the energy sector, specifically on electric sector, the use of coal to generate electricity has increased drastically after that. It's rising so and so forth that we still worldwide still depends upon the coal. So it shows that even if you do not see something on the road, right, tomorrow you run your vehicles on batteries, possibly two-wheelers or four-wheelers. It does not mean that in a short time of span, you are going to go away from fossil fuel, because you are very well know that the renewables cannot sustain your 100% energy. It's not going to happen in near future unless you reduce your population, unless you change the attitude. Right. So if you look at the consumption of energy that is going to grow, and today also you see that we have less than 1% of vehicles which are battery operated vehicles. The data shows. And when you look at more number of vehicles that are going to come on the road, if they start using batteries, then you know that you have to generate electricity into the power plant, and that electricity will be used to charge your vehicle, the batteries, for example. And in the process, you may end up losing a lot of energy. There will be energy loss from conversion. For example, even if you say assume that you convert from coal or petrol, I mean the crude oil or petrol-based power plant or oil-based power plant, or you can have a natural gas-based power plant. If you try to convert that and then into electricity and then again use that electricity to charge your batteries, it's during the conversion you end up losing energy. So specifically, if you look at the overall amount of fossil fuel that you may require to generate that much of electricity, which may run your vehicle, say, same amount of mileage that you would otherwise run using 1 liter of petrol, you may find that we are going to have more required amount of fossil fuel in terms of coal or natural gas, whatever it is, to generate electricity into the power plant. And therefore, that's a very tricky challenge, and then again, if you have battery processing, you required very rare earth elements, etc., to make those batteries. You required mining activities, you required processing of these batteries after their use. So everything will actually end up producing more CO2 if you look at overall process of manufacturing batteries, and there are paper available in the literature. And there is, we have to look at the holistic approach therefore here, right? So that I should back calculate my process of manufacturing anything, and then understand that how much CO2 that I am going to emit in overall process, right? And therefore, it's not very easy problem to look at right now. Of course, it's required a very holistic approach. Now, when you talk about the CO2 capture by the environment, Earth takes care of 50% of CO2 that we emit, or overall, even the atmosphere or Earth also emits CO2 and so forth. And that also Earth environment can take care of that much of CO2, right? So it happens over the land-based CO2. Through land, you can also have the CO2 exchange in the ocean, etc. I mean, the ocean has also its capacity to absorb carbon dioxide that is there into the environment. But whatever CO2 that is being released by human adds up additional burden into the environment, and therefore it becomes difficult for mother nature to capture that CO2 in a short span of time. So this is something that is interesting here. He says that nature emits more CO2 than human, and he said look back behind you, it's also captures CO2 in similar numbers, right? And therefore what you end up having extra that goes into the atmosphere, so that results in additional CO2 concentration into the atmosphere, and that results into increase in temperature of the overall atmosphere. So when you look at this carbon, and therefore immediate goal is required that you have to capture this CO2, and it can be done in a power plant, right there where you generate electricity. And as on today, our 82% of, or more than 80% of our energy mix comes from fossil fuel, coal, oil, natural gas, etc. Right? And about less than 20% comes from other form of energy, right? And it is not going to happen that you suddenly come down to 20% of fossil fuel and 80% of renewable. That's not going to happen in a very short time. I'm saying short time here is means even 30 to 40 years, right? And therefore, the immediate goal that we have in front of us is to capture carbon dioxide right in the power plant. You can capture that, and what you will do with that, you cannot really keep it in your house, right? And you cannot really, as I said, you cannot really convert it everything into the value-added product. The technology is not really commercially available. Of course, there are some plants available, pilot plant, but if you look at these plants, for example, I want to convert CO2 into the methanol, you can understand that there is still a requirement of hydrogen into forming of methanol from CO2 to methanol. And even if that hydrogen you use, you may find that 99% of our hydrogen production as on today comes from fossil fuel. And therefore, that hydrogen that you are going to use to convert CO2 into methanol is ultimately coming from fossil fuel. So therefore, while making that hydrogen, you are again emitting carbon dioxide. So what net that you are converting CO2 into methanol may not necessarily become a carbon net zero or carbon neutral, right? So you have to look at these whole calculations, right? So even if it looks attractive right now to convert CO2 into some of these products, you really understand what the process is and whether that process, each component of that process can generate a carbon neutral balance, and therefore the immediate goal therefore is to capture the CO2 and sequester that. You have to dump it somewhere. One option is that you can dump it onshore, and the other option is that you can actually take it through the pipeline. You can do that through ships, transport through pipelines, and take it to the offshore environment for sequestration, right? Now, there are various pathways available to sequester carbon dioxide. You can sequester carbon dioxide in onshore formations, or you can do that in the offshore. Now, there are various pathways, and I'm saying that not a single solution is viable. I mean, it's not that we have only one solution here. We have to do this in a multiple ways, right? And we have to help nature to capture CO2 and sequester that in a multiple pathways. Yes, so there are multiple pathways. One is that you can actually capture this through the biotic way. You can have algal biomass. That algal biomass can be utilized for biofuels, chemicals, etc. The other pathway could be that you can capture that CO2 into the permafrost. You can capture that CO2 into the depleted coal fields. You can also produce methane out of that. People are also looking capturing CO2 into the depleted oil and gas fields onshore, where the oil has been already produced and there is not much oil left. So you can use that reservoir to store your carbon dioxide. You have large pores over network over their porous bed, and therefore you can sequester that CO2 into these depleted oil fields. The other option that you can actually sequester carbon dioxide into the saline aquifers, where the aquifers can be a potential locations where CO2 can get mineralized very fast, and therefore it remains in the solid form. You can actually form carbonates over there in situ, and therefore it becomes more stable form of CO2 sequestration. The other CO2 sequestration could be in the form of hydrates. You can actually sequester that in the ocean in the form of hydrates. Offshore, you can also sequester that in the form of liquid pools. You can do that below the sediments or above the sediments, potentially, possibly potentially below the sediments, seabed sediments. And then you can safely store that, for millions of years. And as I said, you can actually use that CO2 also to convert in various byproduct, urea, polymers, biofuels, etc. But this is the wrong way to go, and really want to have renewable resources to really make these things happen, right? So when you talk about ocean, which I'm going to discuss that, but you can, in the ocean, you can have different pathways where you can actually transport that through the ship, and you can actually do that at a various depth, and why it is potentially promising, that I will discuss in a subsequent time, and then you can actually do that in a form of liquid CO2. You can do that in a solid hydrate form. You can convert that in the carbonate, etc., because you have salt water, and that can actually help you to convert it into the carbonate easily. So various methods are being there, and if you look at this technology readiness level of various methods, you can see that when you talk about technology readiness level, you start from concept TRL1 to about commercialization TRL9, and from TRL1 to TRL9 you have various steps from formulation. You have proof of concept, lab prototype, lab scale plant. You can also have pilot plant. You can have demonstration, and you can have commercial refinement requirement, if any, and then you can go for commercialization. So if you look at the commercialization, there is various methods are very well commercialized. For example, CO2 sequestration for onshore applications, specifically for enhanced oil recovery, is very well commercialized to store carbon dioxide. You can use saline formations to store CO2, very well commercialized. You can actually transport CO2 into the liquid form, by ships, so that's also been done. Transport onshore and offshore through the pipeline is also being done. Pre-combustion capture of natural gas processing, it's also being done. Post-combustion capture through power plants using amines is also being done. There are various methods which have been done on the demonstration basis. So you can see that I'm not really going to read many of these methods, but you can see that there is a whole lot of methods available in the basket, and you have to pick which method is suitable for your application, right? So as I said, that it's not that there is only one solution to capture and store CO2, right? All these methods depend upon the location and the source of CO2 from where you are actually producing carbon dioxide, right? Now, therefore, when we talk about this carbon dioxide capture and sequestration, once you do that capture, you can actually capture it directly from the flue gas, or stationary power plant, stationary point source. You can do that from the air. Direct air capture are one of the technologies where people are looking at capturing carbon dioxide from the air, right? So there you have 420 ppm of
संतोष
CO2 molecule.
और
Hello,
अनुराग जी गए हैं महादेवन जी के पास समझने के लिए
hello. Yeah.
Sir, I think by mistake some participants unmuted, it seems.
Okay. Yeah.
Okay, it's okay, sir. Sorry.
Yeah. So you can actually convert that CO2 as I said, right? And then one of the other applications that you can store carbon dioxide into the subsurface reservoir for enhanced oil recovery or sequestration purpose, right? So CO2 capture is not a very new process. It's been there since long time. Oil and gas industry is using that for separation of carbon dioxide from natural gas and for industrial application. But in recent times, the focus has been changed primarily to look at climate issues. So now the similar methods which are there already available, some of these methods can be explored now to capture carbon dioxide from flue gas or something like that. So before we start and understand that, one has to understand from this phase diagram that carbon dioxide has a specific phase diagram where CO2 can be in the form of liquid, solid, and gas. And there is also supercritical fluid. And there is a critical point which is about 300 degree Kelvin, that's about 27 degree centigrade, and about 100 bar of pressure, that comes to about 1500 psi. And that's the critical point for carbon dioxide. So any condition of pressure and temperature makes the CO2 into the form of liquid over here, and any condition that is over here makes the CO2 in the form of gas, and any condition that is over here makes the CO2 in the form of liquid, right? Liquid also has a very peculiar property when you talk about compressibility factor. So this is a graph that shows that, this compressibility of hydrogen is always more than 1 as the pressure increases, right? And at STP, all the gases remains to be ideal, and therefore Z, which is a compressibility factor, PV equal to Z nRT. So that Z is 1 for most of the gases at standard temperature and pressure condition. However, when the pressure increases, the Z will change for various of these gases. And you can see for hydrogen, the Z is always more than 1. So it's always been increasing continuously. For nitrogen, the Z decreases and then start rising beyond 1. For methane is again decreases and start rising again after 1, somewhere about close to 380 atmosphere. For carbon dioxide, the Z decreases as the pressure increases, and this is again at a constant temperature at 0 degree centigrade. And as pressure increases, the Z start increasing again. That means Z value less than 1 indicates that the gas is reasonably compressible. And more the Z is less than 1, the gas becomes more compressible in nature. And when Z is more than 1, gas becomes incompressible. So if you can see that when Z is more than 1, hydrogen is incompressible, and therefore it is very challenging to store generally. As far as CO2 or methane is concerned, the Z decreases as the pressure increases at certain condition. Say in case of methane, it is minimum has attained about 200 atmosphere. So if you find that methane can be stored very economically to about 180 to 200 atmosphere. So most of the CNG kits that we have in the car, they pressurize the methane close to about 180 to 200 atmosphere, because that is where you have a maximum amount of volume that you can attain. And then beyond that, every molecule of additional CO2, CH4 can increase the volume, And same thing is for carbon dioxide. So in carbon dioxide, the maximum amount of volume that you can attain is close to about 50 atmosphere, that's where the minima of Z is taken, right? So this is very important to understand that some of these properties of CO2 are very important to design your methodologies for transportation, capture, or storage. Now, this is a typical flue gas, so amount of flue gas that we generate in a power plant, exhaust, right? So most of these exhaust power plant, which have a chimney primarily from coal-based power plant, can have primarily nitrogen, which is about 60 to 65% in most of these cases. The carbon dioxide can vary depending upon the nature of the coal that is there. It can vary from about 18% to about 20%. And then you have oxygen, little bit of it, you have moisture, and you have other gases like, sulfur dioxide, sulfur trioxide. Though it is very small in amount, you can see that this is very small in amount. But this small amount can be more problematic even for the chimneys, right? So most of these chimneys actually works at high temperature to ensure that the sulfur dioxide does not deposit into their chimney. Otherwise, they start corroding. And therefore, the temperature is reasonably kept high, right? So when we look at these CO2 capture, processes, so there have been various processes available in the uh, market, and some of these processes are under development. However, a very well utilized process is the post combustion capture, right? Now we have to understand that when and where one can capture the carbon dioxide, whether you have to capture carbon dioxide before you do a combustion, or whether you have to capture the carbon dioxide after you do a combustion, right? So generally there are three major methods available. So one is the pre-combustion capture of CO2, where one can actually capture carbon dioxide before the coal can be utilized into the power plant. So here what is done is that the fuel is being injected into a gasifier, where you supply oxygen or air, and then partially oxidize this fuel, and then using that you generate a syngas, which is a primarily a mixture of hydrogen and carbon dioxide. And that syngas, after you do a processing, where you have now a CO2 rich fluid, so this becomes a CO2 rich fluid. So when you have this CO2 rich fluid, you can capture that CO2, reasonably easy, because here the concentration of CO2 is more, reasonably more than typically a post combustion power plant. And then it becomes easy to capture that carbon dioxide and then store that, and then use that hydrogen to generate electricity, right? Now, this requires integrated gasification combined cycle power plant, and these are very less in numbers, and therefore, though this technology is there, some of these plants are available, some of these places, but these are not widely acceptable, because you need some more additional investment and modification into the power plant to make sure that you can actually use this pre-combustion capture, right? So it also results in more amount of cost that is required to capture carbon dioxide, and it can go to about $60 per ton. And therefore, we need, and then this is a capture plant, you have to do a sequestration and then processing and so on and so forth. So the overall cost may go even 150 ton or so, and that's not something that is very attractive right now, right? Now, therefore, it's also challenging to use a hydrogen rich fuel, right? So you have more hydrogen, safeties are there, issues, heat transfer challenges are there. You may end up losing a lot of energy also in doing that, so there are certain challenges available, and require better materials to address those challenges, right? So this is still not very widely accepted because of various challenges available. The other, which is reasonably accepted, is post combustion capture, where you do a combustion of fuel like coal or natural gas, and then whatever exhaust stream that you have, though it contains less amount of carbon dioxide, but still you can try to capture that carbon dioxide using whatever known process available, and then transfer that CO2 into the storage site, right? So here you do not need much changes into the power plant, but you can actually add additional unit where you can capture carbon dioxide, right? As I said, the challenging task is that low concentration of carbon dioxide into the exhaust stream, right? So you again have to understand that how you can make sure that you increase the CO2 into the exhaust stream. So there is another method which is called the oxy-fuel combustion capture. So where you actually do uh, primarily a very efficient combustion of fuel using oxygen, right? So if you supply a very pure oxygen into the chamber, so what can possibly happen that after you combustion of fuel happens, you get exhaust gas and it may have a more amount of carbon dioxide. Typically, it can go and range to about 50% of CO2 into the exhaust stream. And when you have a high amount of CO2 into the exhaust stream, then you can reasonably capture that CO2 easily because you have enough amount of CO2 to capture. And the process becomes more efficient in that sense, right? So in oxygen fuel combustion, the only requirement is that you have to supply very pure oxygen, right? So it primarily results in the production of water vapor and CO2 that can easily be separated. One of the challenge here is that it may have a high flame temperature. So it's also typically possible that you may have a loss of energy if you do not really control that oxygen movement into the chamber. This is primarily used in the steel making industry or metal cutting industry. And then people are trying to see that if oxy fuel combustion can be utilized in some of these power plants, can we have a better capture of CO2 from the exhaust stream, right? So this is a overview of various CO2 capture process where you can see that you can have a post-combustion capture, pre-combustion capture, oxy-fuel combustion, and you can also have industrial processes where like you have a natural gas production plant, etc., etc. That you may have, right, from power plant through pre-combustion or post-combustion capture or oxy-fuel combustion capture to from various industrial processes where you require coal, gas, or biomass, and then this CO2 can be captured and compressed and then transported specifically for a sequestration purpose, right? Now, sequestration, and these are some of these plants available. I will just skip that. So various methods are available. You can actually use amine-based systems. My focus is not there today in discussing in more detail about that. But you have monoethanolamine, diethanolamine, methyl diethanolamine, and you can see that you may have various concentration of some of these chemicals to be utilized to capture carbon dioxide, right? And these are very industrially acceptable processes available. And therefore, even though overall amine may not necessarily results in carbon neutral process, but reasonably they are still very attractive method because of its acceptance in the industry, right, as compared to other methods. Right, so this is some of these power plants which are using carbon capture methods. For example, here they are using amine solvents to capture CO2, and they are actually capturing 114 kilotons of CO2 to transport and sequester that, store that CO2. So some of the power plants and examples that are available. For example, this is Norway Slipner Japan project where they are sequestering carbon dioxide into the ocean. This is Japan Tamakomai project where it has been installed in 2012 and revitalized in 2018 to actually capture carbon dioxide and sequester that, right? So some of these examples shows that yes, there is a promise of some of these technologies. And I will just skip that. We are actually doing some of this work in one of the power plant near Chennai. So we have actually got a patent on that CO2 capture process, and we actually set up a plan for that to capture carbon dioxide. It's now some of these tests has to be done in next month after the cyclone is over. So once you do that, once you capture that carbon dioxide, you have to ensure that you have to transfer that from source to storage sites. Either you can do that through the pipeline, you can do that through the ships and sink, right? So the transportation part, I'm not really going in detail right now, but what I'm going to do that, I'll show you my next talk. Sorry, I'll just share that. Wait a minute. Okay, okay, okay. Now let us come on this here. Okay. Now, so this is what it is. No, so the next talks, I mean, I just made it into the two parts. So the next talk will focus on understanding what we have to do with the carbon dioxide. All right. Now, once you capture that CO2, as I said, you have to store that. You have to convert that CO2 into any value-added product. And again, uh, I'm not sure whether we can do that in a very short time here. Short time means 30 years or 40 years. So immediate goal is that you have to get rid of the CO2 either onshore or offshore. Onshore, you can do that in a depleted oil and gas reservoir or in an aquifer. And offshore, which you can do that into the ocean. Now, so I just skip that. Now, I want to tell you before I go and understand why the ocean can be a more potential location for storage of carbon dioxide. Now, methane is a more potent greenhouse gas as compared to carbon dioxide. That everybody is aware of it, right? It has more of 30 times more potential to address a climate change than carbon dioxide. Now, methane has been released by nature for millions of years, specifically into the sea, where there are organisms which are there, marine life is there, etc., etc. And they have been releasing methane for millions of years into the ocean environment. Mother Nature had a solution for that. If today Mother Nature did not do that, we would have ended up having significantly high temperature in the earth because of methane into the atmosphere. What Mother Nature had done, that Mother Nature has captured that methane in the form of solid hydrate. You can see that how they looks like, right? So gas hydrate accumulation, in which is primarily a natural gas, which is a methane, has been there worldwide in all the oceans. In Andaman Nicobar Island, we have that. KG Basin, we have that, etc. And worldwide, it's available in the ocean. Methane hydrates are everywhere. And that's because Mother Nature has captured that methane in the form of hydrate. The hydrates are a ice-like compound, which you can see over here, which are actually in solid form. So if you look at the amount of carbon content in the nature, 53% of the carbon content is actually accumulated in the hydrates. So you can see that most of this methane, which is there in the hydrate, accumulates significant amount of carbon. That indicates that the nature had itself taken care of these climate issues by itself by forming hydrate. Now one has to understand how this methane come. The methane might have come from the thermogenic way, where methane might have shifted from below the earth crust, or it can actually have a biogenic methane, which can secreted toward the surface of the earth at the ocean. And most of this methane get accumulated in the form of hydrate. Now, what is hydrate? Hydrate typically form at high pressure and low temperature conditions when a gas comes in contact with the water molecule. The high pressure conditions appears to happen in the ocean because of hydrostatic pressure, and low temperature because you have about 4 degrees centigrade temperature, and therefore high pressure and low temperature conditions prevails at the bottom of the ocean, which are favorable to form hydrate for specifically for any gas, in this case here the methane, right? Now, what are these hydrates? So hydrates are a cage-like compound. One can see over here. We have various structure of hydrate. We have S1 hydrate, S2 hydrate, or SH hydrate. And based on number of molecules that get part to form the cages, you can have a 12 pentagon cages. You can see over here, you can have a cage which is formed by 12 pentagon and 2 hexagon like this. And when 2 of these cages and 6 of these cages comes together, they form a structure 1 hydrate. And likewise, your structure 2 and structure H hydrate. I'm not really going in more detail. But when this cage, you can understand these are rooms, empty rooms. And the gas molecule like methane here goes into these cages, and they become stable. And this cage looks like a ice compound. It looks like ice, but it's not really ice, right? Now, this is typically a phase diagram for any hydrate to form. This is a solid line which separates out a hydrate stable zone. You have a hydrate stable zone over here on the left hand side. This is a pressure temperature condition, and this is a hydrate unstable zone. So any condition over here, make sure that you have a stable hydrate zone, and any condition over here, make sure that you have an unstable hydrate zone. This typically happens at a low temperature condition. So you have this zone 1 or zone 2 reasonably more stable because the temperatures are more low here, and pressures are much higher, because the more higher pressure, more stable the hydrate is, right? So when you look at this hydrate stability with respect to CO2 gas. You know, uh, this is a very important figure that you can see. I'm not really going in detail with this figure, but if you look at this figure here, so if you separate out, so this is a simple phase diagram. I think everybody studies that in a 12th standard. So you need not to be a chemical engineer to understand that. But you look at this pressure and temperature, and this is a solid line which separates out CO2 gas and liquid. So this is a CO2 gas, this is a CO2 liquid on this phase, and this is supercritical CO2. And this red line which separates out CO2 hydrate over here, CO2 hydrate. Now, the idea here is that if Mother Nature can sequester methane in the form of methane hydrate or natural gas hydrate into the ocean for millions of years without affecting the environment, can we sequester carbon dioxide into the ocean and make it into the solid form? Right. So when it is in the solid form, it need not necessarily affect the marine lives, because it is going to convert over a period of time, become mineral, because your salt there, your calcium carbonate, calcium chloride, etc., etc. And Mother Nature has a way to convert that CO2 into carbonates in a reasonable time scale. Now, this CO2 hydrate, if you look at this, so it indicates that at a certain temperature and pressure condition over here. So any condition on the left-hand side, forget about this green line and forget about this methane curve and propane curve. Look at this only CO2 hydrate curve. So any condition on the left-hand side indicates the stable zone of hydrate. And this condition on the right-hand side indicates the unstable zone of hydrate. So it indicates that if I try to have a condition of say 10 megapascal and say about 4 degrees centigrade somewhere here. So look at this cursor here. So if I have this condition in the ocean, it indicates that the CO2 will become a liquid. So if you look at the solid line, it shows that the CO2 becomes a liquid at this condition, and CO2 liquid will form hydrate into the ocean at this condition. If I have a condition less than 5 megapascal at say 4 degrees centigrade somewhere here, the CO2 will become a gas, and then the hydrate may form from the gaseous carbon dioxide. Right. So this is a very important, understanding from where at what pressure and temperature condition CO2 will become a liquid and CO2 will remain in a gas state. Right. And in the way how the CO2 is going to go and interact with the water molecule to form a hydrate. Right. So this indicates that, simple diagram over here. So this is a stability curve on a very logarithmic scale, and it shows that this condition is your initial condition where it's an unstable zone, and as you go and move your condition into this point over here B, you end up having a hydrate formation. B prime is also having a hydrate formation. And if you decrease the pressure beyond certain pressure, then the stability of hydrate will get destabilized, and the pressure, because of reduction in the pressure, the hydrate may get dissociate, right? So you may have only gas and water, or ice here in this case, right? This is ice and gas. You can have water and CO2 gas. Here you have a CO2 hydrate and CO2 liquid. You have CO2 hydrate and CO2 gas, right? So one can understand that this phase diagram provides an very important insights into how the CO2 hydrates may form at what condition, right? Now, let us look at the ocean condition. So if I want to sequester that carbon dioxide that I capture from power plant, and then I want to inject that into the ocean. Of course, I'm not really going to inject into the ocean. I'm not going to do that in the ocean water. Remember that. And therefore, if you think that I'm going to inject that into the ocean, no, I'm not going to do that. But let us understand the science behind it. What will happen if I do that into the ocean at certain depth? So this is oceanic depth, starting from 0 meter to about say 1400 meter, right? The corresponding pressure is shown here. And this is a thermocline. Thermocline is a temperature profile into the ocean. So it shows that the temperature at certain depth, say about 800 meter, the temperature is about 4 degrees centigrade. That is about 7 to 78, so 4 to 5 degrees centigrade, right? This is the temperature at say about 800 meter depth, right? And temperature starts from the ocean surface. That is about 298, say about 25 degrees centigrade. It decreases as you go deeper and deeper into the ocean, and it becomes about 4 degrees centigrade to about say 800 meter to 1000 meter. This is for Gulf of Mexico. And then you have this CO2 hydrate saline water condition, hydrate stability zone. And how to read this diagram, right? So if I say that I have a condition at P1, so at this depth, What is the depth? Is about 100 meter. So at 100 meter, what is the temperature that I should read is about 292 degrees centigrade. This is a temperature at 200 at 100 meter depth. That is 292 degree Kelvin. Sorry, degree Kelvin. That's about 15 degree, about 25 degrees centigrade. Right. And then as you go deeper, say P2, as you go deeper into the ocean, your temperature will decline to about 287 degree Kelvin. As you go deeper, it's about P3, let us say, and the temperature is about corresponding to about 282 degree Kelvin. As you go deeper, the corresponding temperature over here is 4 degrees centigrade. Here you see this, you go take this line like this, you have to go on the horizontal way, not on the vertical way. So this temperature is about 270 degree Kelvin. At P5, at this depth, say about 1200 meter, the temperature is about 4 degrees centigrade. So you have to go and cut this thermocline. So you can easily understand from the thermocline that how you go deeper and deeper, how the temperature can be recorded. Now, pressure wise, it's a simple, you can just correspondingly look at on the secondary y-axis, that is your pressure, right? So at P5, I can say that the temperature is about 4 degree K or 277 degree Kelvin, and the pressure is about somewhere about 10 to 12, 11 megapascal or 11,000 kilopascal, right? So this is 11 megapascal, right? And if you look at this CO2 had a stability curve, this solid blue line, one can understand from this that at P2, though it looks like that it is in the stable hydrate zone on the left hand side, actually the temperature over here is about 287 degree Kelvin. And when you look at this temperature, it falls outside the stability zone, right? So therefore at P2, the hydrate is not stable. I mean, when I inject carbon dioxide, and if it reacts with water to form hydrate, it will not form hydrate at this condition because the temperature is outside the zone of this hydrate stability curve. Let us look at the P3 or let us look at the P4. P4, the temperature is somewhere here about 282 to 78 Kelvin, and pressure is again about 8 megapascal or 8,000 kilopascal. This condition indicates that the temperature and pressure conditions are well on the left hand side of this curve, which indicates that the injection point at P4 could result in the hydrate formation of CO2 here in this case, right? And this is here the CO2 gas liquid line. This is a CO2 liquid line. So at P4, one can say that this condition will show that at P4, CO2, if it is injected, will become a liquid CO2 and it will then form hydrate with the water. So it will first have a phase change from gas to liquid at P4, and then it will form the hydrate. For example, at P1, if I inject carbon dioxide at P1, the temperature is such that at this condition, if you look at this CO2 gas liquid line, at this condition it falls on this zone, and therefore the CO2 will remain in a gaseous phase. As you go deeper and deeper, the CO2 will become liquid and you end up forming hydrate from the liquid phase, right? So here, based on the intersection of this hydrate curve, hydrate stability curve, and the thermocline, one can say that the minimum pressure required to form hydrate or minimum depth that is required to form hydrate as far as CO2 is concerned is about 490 meter, or let us say approximately 500 meter. So that means minimum 500 meter is required that you should inject carbon dioxide into the ocean to form CO2 hydrate. Now the CO2 hydrate, once they form, it's shown that in the literature that the CO2 hydrate have a slightly higher density than the seawater. Seawater density is roughly about 1000 kg per meter cube. Of course, it is more than that, slightly more than that. But assuming it is a 1000 kg per, 1000 gram per liter or 1 kg per liter, the density of hydrate of CO2 is more than that. And therefore, once CO2 hydrate will form, it will go down into the sea, right? However, CO2 hydrate is not a very quick process. It's a stochastic process. It's a random process. And therefore, of course, you do not want to form CO2 hydrates into the ocean, right? So not into the water ultimately, right? So what are the other potential look at? Potential possibilities. Now, this is a very interesting diagram. You know, you look at the density of the CO2 and with respect to temperature. And these are the pressure profile, you know, this 3 megapascal, 6 megapascal, 9 megapascal, 12, 25, 35, right? and you have this temperature on this line. And let us assume that you are injecting carbon dioxide at say 800-meter depth, and assuming that your temperature is say about 4 degrees centigrade somewhere here, right? So somewhere here you have, right? So if you look at the pressure and see some of these isocores here at pressure profile, some of this pressure profile, this is 9 megapascal. So if you want to read your density of the CO2 at say 9 megapascal and 4 degrees centigrade, these points should come over here somewhere, say about 950 kg per meter cube or something like that, which is lower than 1000 kg per meter cube, which is a typical density of water or seawater, for example. So a certain pressure, for example, if you look at this 25 megapascal, you take this line over here and read the density at say 4 degrees centigrade, it comes to about say close to maybe 1100 or 1050 kg per meter cube or slightly around that time. And you can see that at this point, the density of the CO2 becomes more denser than the water density. And therefore, there are certain conditions of pressure like highlighted over here, which are possibly pressure conditions at 4 degrees centigrade where the density of CO2 may become more than the density of the water. Now, this has a very important implications for CO2 sequestration, right? Now, when you look at this in a sense of ocean, seabed. Now, as I said, like, I do not want to sequester the CO2 into the ocean. Of course, that's not something that I'm looking at it. So I want to sequester that into the sediments, below the sediments. Now, below the sediments, you can also look at the thermocline. So as I said, the thermocline, so this is a hypothetical 3,500 meter depth, and the temperature decreases to about 4 degrees centigrade somewhere here, and temperature continues to rise as thermocline increases. You can see that temperature continues to rise. Now, when you look at this, temperature increase slowly, you will find that because of the thermal gradient, the temperature goes on increasing. You can also have a hydrate stability curve plotted over here. So this is a temperature. This is a hydrostatic pressure. And if you look at this curve, it may intersect somewhere here. So it indicates that you have a zone where hydrate may form into the sea. That's called as a hydrate forming zone or hydrate formation zone, HFZ. You can see over here, right? So beyond that, if you try to inject that, say about 400 meter somewhere here, below the seabed, below the seabed. So somewhere here, 3,500 plus another 500 meters somewhere here. So below the below the seabed, 500 meter, it's possible that the temperature may be away from your hydrate stability zone. And therefore, even though if you inject carbon dioxide, it's possible that it may not form hydrate, right? However, you look at this another figure here. Now, this figure shows the density of water, which is close to about 1040 kg per meter cube. So density of water is reasonably of that order because you have seawater, and then density of water remains almost the same even if there is a water in the sediments, in the below the subsea sediments, right? However, look at the density of the carbon dioxide. As the depth increases, pressure increases, and density of the carbon dioxide also increases. Because you see that I have shown you in this graph, the density of the carbon dioxide increases as the pressure increases. You have this different pressure profile, and density of the carbon dioxide has found to be more than water at certain pressure conditions. Right, so at 4 degrees centigrade, if I try to look at the density of the carbon dioxide, it has shown that density of the carbon dioxide increases continuously. At certain depth, it becomes more than water. What is that depth? That depth is about 2,800 meters, somewhere here. So if you try to inject carbon dioxide say at Q1 point, the CO2 is, even though it is a liquid, it will be lighter than the water, and it is possible that the CO2 plume may rise. They may come up because of these are denser. Water, simple, say we have water and coconut water and water. Water is denser, so it will remain down. Coconut water is lighter in density, so it will be at the up, right? So similarly, this is a CO2 liquid, but at this condition, density is low, and therefore it will be lighter than the water and it will tend to rise upward. However, at a certain depth, say Q2, the density of the CO2 is heavier than the seawater, And if you try to inject that carbon dioxide at certain density, at certain depth, which is about 3,000 meter, the CO2 plume may sink. It's going to go down. Right. Now, as I said, I do not want to inject that into the seawater. I will inject that into the sediments. How it looks like in the sediments. So if I inject that, so again, here you see the density of the carbon dioxide will decrease because now temperature is increasing over here. You can see here, temperature is increasing, so carbon dioxide density will tend to decrease. And at a certain point, the density of the carbon dioxide will be lower than the water. And therefore, in this zone, specifically, if you look at this zone, the density of the carbon dioxide is more than the water. And therefore, if you inject carbon dioxide somewhere here, it will sink because it is heavier than the water. However, if we try to inject that somewhere here, in this condition, the density of the carbon dioxide is more, and therefore it will rise, because it is lighter than the water, and it will therefore it is rise. However, the moment it comes somewhere here and try to escape again towards upward side, it will feel heavier because here at this condition, as I said, the density of the carbon dioxide is more based on this graph is more than the water. So what will happen that this zone will remain a permanent sink for carbon dioxide into the sediments by virtue of its density driven sink mechanism. Here, this zone is called as a non-buoyancy zone. That means here the CO2 will not rise because of its heavier density of carbon dioxide than the water. Now, this temperature of the sea is reasonably 4 degrees centigrade, is not going to change, right? And therefore, if we exploit that for sequestration of carbon dioxide, the condition in the sediments indicates that you have a better sink of carbon dioxide. And in any kind of seismic activity, it's not going to happen that suddenly the seabed temperature will rise to 25 degrees centigrade. No, it may jump a little bit of it, but it is not going to affect too much of density of the carbon dioxide. And therefore, this zone provides a very potential location to sequester carbon dioxide permanently into the liquid CO2 form. However, as I said in my earlier discussion, that liquid CO2 will not remain liquid CO2 over there, but it is going to react with water and form hydrates. And as I said, hydrates are a solid-like compound. So if you are going to inject that at a certain depth in a zone where you have liquid CO2, even though it is lighter, it will try to rise. But in that process, what will happen? That hydrate will form. And once hydrates are a solid-like compound, they may provide a permeability barrier because of hydrate pore blocking. And here you have additional gravitation barrier because here carbon dioxide is more denser than the water. So it will try to sink. So it will remain permanently trapped because of two simultaneous mechanism: gravitational barrier because of higher CO2 density than the water at certain depth, and permeability barrier because you have a carbon dioxide that is getting converted into the hydrate form. And you can also have additives which you can use it into the lab and form or increase the hydrate formation faster once you sequester that into the ocean. So because of this, the ocean provides a very potential location to sequester carbon dioxide. As I told you that methane hydrates have been there for millions of years without affecting the mother nature. So you may worry that what will happen, marine life, etc. I'm not going to sequester that into the ocean. As I said, I'm going to do that into the below the bed. Now, question remains that what will happen to the CO2? CO2 will form hydrates one way. CO2 that is getting injected will may get converted into the minerals also because you have carbon dioxide, you have the salt, NaCl, you have calcium chloride, etc., etc. So that may result in some kind of mineralization. Of course, more studies are required in that direction. Also, it's possible. So this gives a very different schematic which shows that what are potential ways that you can sequester CO2 into the ocean. As I already told you that you can do that in a form of hydrate. You can do that moles of hydrates that you dump it into the ocean. Of course, we need more studies. What will happen to the CO2 hydrate mold? But I can do that below the sediments. Likewise, you can do that even if the CO2 plume will rise. The non-buoyancy zone will ensure that the CO2 will remain trapped permanently because of heavier density of the carbon dioxide. And you can also do that into the certain depth in the form of liquid carbon dioxide. And it's possible that you can have a hydrate, a layer formed onto the top of liquid CO2 pool permanently, so that this will remain in the form of liquid CO2. Top of it, it will have a hydrate layer, like a solid ice layer. You know that in Dal Lake, when the temperature decreases, you have a solid ice layer that forms, and people want to be walking on that. You have below water, right? So similarly, in the ocean, it's possible that you may have a liquid CO2 pool, and you can actually have a solid hydrate layer that is getting formed on the top of liquid CO2 pool. Right, so this is one potential pathway. Of course, it requires much higher depth, that is to be done. Now the technologies are there, the oil and gas technologies that are already there into the basket it easily been exploited to do a CO2 sequestration, right? So it's not that how do I do that, right? So the technologies are available, pipelines are being laid, etc. Existing pipeline in offshore conditions can be utilized to sequester carbon dioxide into the ocean. Now, in various locations, we have identified, this has been published in Energy and Fuel in 2023. Various locations based on the bathymetry data, we can look at various potential sites where CO2 sequestration can be done, across the globe. And you can also have some of the trench, which are potential locations to inject carbon dioxide in the liquid form. And of course, as I said, that will continue to get converted into some kind of other materials, carbonates, etc. So that again required more studies as far as research is concerned. So you can actually have different possibilities of how the CO2 hydrate is going to form. You can have a class 1, say subsea sedimentary basins below 3000 meter. You can also do that onshore on the sea floor, where you have seawater, CO2 hydrate, and liquid water and sediments. Here, CO2 hydrate can be sandwiched between the pore water sediments or liquid CO2 and sediments. And you can also have a class 3 kind of reservoir where you can actually have liquid CO2, and on the top of it, you have thin hydrate crust that is actually avoiding the liquid CO2 going into the water. And remember that this is a higher in density. So even if this breaks out, it will again get repaired by its virtue of its own mechanism, and that liquid CO2 will not really come out, right? So this is something that we can do using different pathways. Like you can have injection wells, vertical injection well, you can have a horizontal injection well, you can have a multilateral injection well that you can do using current technologies in oil and gas industries. You can do that using a ship, you can actually do this on the sea floor, likewise, So some of these methods has to be utilized and explored to see how the CO2 sequestration can be done. Now, what will happen, so anyway, I think I'll just quickly run through some of the studies that we have done at the lab scale. So we have looked at impact of various sand particles to understand what will happen to form hydrate from the liquid CO2. So this is a 6 megapascal and 276 degree Kelvin, that what we have done experiments at using a reactor, and we have a sand bed using a different kind of see sand size. You take that from Marina Beach and you sieve that in a different size, and really understand that what will happen with the different particle size, how they are going to affect my hydrate formation kinetics, right? So we have observed that you can actually form hydrates into these lab scale methods using reactors if you mimic some of this condition at the lab scale, right? And then we have observed that the seawater, because you have salt, that may affect the kinetics of hydrate formation. And you have pure water, which is reasonably favorable to form hydrates. But when you have seawater, it's been found that the salt in the water can inhibit hydrate formation. But of course, at the end, you end up forming hydrates, right? So that's not really an issue. But you can also have a promoter. So you can use some kind of hydrate promoters which can augment and accelerate the hydrate formation in a seawater, right? So I will show you some of these examples in subsequent slides, right? So we also looked at the studies using bentonite clays, because that's again sample system. For example, in KG Basin, Krishna Godavari basin, you can also have some kind of clays along with the sand and silt. So we can actually carry out some of these experiments at the lab scale using conditions that mimics the liquid CO2, using the conditions that mimics the gaseous CO2, etc. And we also formed hydrate using some kind of promoters. Like here you have these surfactants, for example, sodium butyl sulfate. And it has been observed that when you use some of these surfactants, they may promote hydrate formation. You can see that, in this, for example, in this figure, you have the seawater. This is a line over here. And when you have this seawater plus SDS, you can actually see the gas uptake. This is a bentonite. This is a bentonite, and this is a bentonite plus SDS. So this is a bentonite and seawater, and this is a bentonite plus surfactant. So you can see that the hydrate formation is reasonably very fast. The gas uptake into the hydrate formation increases drastically. When you use some kind of surfactants, right? So some of these studies are being done. Using various methods at the lab condition, and it has been found that when you look at this effect of surfactants, or some of these promoters, they may provide some additional advantage. Sometimes surfactants may not necessarily provide advantage because you may end up having a foam rather than surfactant helping you out. Right, so you have to optimize the concentration of some of these promoters to ensure that you have favorable hydrate formation. Now we have done some of these experiments at the lab. You can see this reactor. So this is a hydrate. This is not ice actually. This is a CO2 hydrate that we formed in the seawater. This is a bentonite in the seawater, and this is a surfactant along with the bentonite and seawater. You can see that this becomes very fluffy. When you use a seawater surfactants along with the seawater, this becomes very fluffy. And without surfactants, you may have very solid, rigid block of hydrate. This is not ice because these experiments are done to about 3 to 4 degrees centigrade. Right. So at this condition, ice doesn't form, and you can actually look at these signatures of pressure and temperature, which shows hydrate formation. Right. So some of these experiments are done in the lab scale. I'm not really going in detail about that, but rheology plays an important role here. That means the fluid properties, how the hydrate slurry may behave differently. For example, it's possible that you are injecting into the slopy or muddy terrain, and it's possible that hydrate getting formed and it may, roll over. So you need to understand the rheology part of it. How hydrate will behave differently when they are being formed along with the clays. Right. So for this, we have carried out some experiments using the rheometer, and we formed the hydrate in situ. So we looked at various conditions of gaseous CO2. This is a condition where the hydrate formed from the gaseous condition. This is a liquid-based carbon dioxide at this condition, and we carried out various experiments, using CO2 from gas phase and liquid phase to look at the rheology, how the flow behavior or viscosity will change, etc. So I'm not really going in detail about that. But again, we looked at the rheology in terms of clay, bentonite clays and promoters. We also looked at the promoters, and we found out that when you use the promoters, the yield stress may end up increasing. The yield point may increase reasonably well. You can see over here, right? So yield stress is a stress that is required to flow a system, right? So some of these promoters can provide added advantage of having an increased yield stress, and therefore they are favorable in some of the situations. So again, you can see that how the hydrate is getting formed. You can see the bubble coming out from these videos, and this is how the hydrate is formed into the rheometer in situ. This is a very small space, so you can see that bubble coming out. You can see the hydrate, some of these conditions. So this is a very specific example that how you can mimic some of this condition at the lab scale and understand that what will happen if I inject carbon dioxide into the environment, either onshore or offshore. In this condition, I'm talking about seawater or offshore condition, and therefore some of these studies provides very important insights into hydrate formation. We have looked at various promoters. I'm not really going in detail, so you can actually do an injection using horizontal well condition. You can inject that in a well. This is a CO2 injection well. This is a chemical injection well, and you can form the hydrate, at this zone. Right. So this is something that is possibly one mechanism of CO2 sequestration into the sediments. So you can do that injection of carbon dioxide beyond 500 meter to 1000 meter sea depth. All right. So that's something that is potentially one way to get rid of carbon dioxide from the environment. What will happen to the pH? Yes, if you do not do this properly, and if the CO2 may end up leaking into the ocean water, the local pH may change, and which you do not want that. So more care must be taken. However, if you look at the overall capacity of the carbon dioxide injection into the ocean, it's huge. And it is said that you are talking about only capturing uh, uh, you know uh, about 1200 gigatons of CO2 in next 30 to 40 years. However, the entire sea volume may require 240,000 gigatons of carbon dioxide to reduce pH by 1 unit. And from this, you can see that. So just 1 unit, if you want to change the pH, you require huge amount of CO2. And we are not, so this is like 190,000 gigaton of CO2 to reduce pH by 2 units, overall sea capacity. We are looking at only 1200 gigatons, much lower than this. So therefore, it is expected that the pH may not change. And as I said, over a period of time, the CO2 may change and get converted into the carbonates, right? So this is something that one has to understand, that what will happen with the CO2. So with this, I think I should stop my discussion so that I can give some more time for any questions that you may have. So what we have looked at, the CO2 capture process, how that can be done using some of these methodologies available, pre-combustion capture, post-combustion capture, or oxy-fuel capture, and then get rid of that CO2. Either you can inject that onshore, you can do that in a depleted oil and gas reservoirs, or you can do that in offshore to sequester CO2 in the form of hydrates, right? So thank you so much, and let me know if you have any questions.
Yeah.
Hmm.
Participants can directly interact with Professor Jitendra Sangwai. Anybody has any questions, you can directly interact with the speaker.
Sir, one question is there. Sir, like you're saying that means most of the CO2 is getting injected under the sea basically. But nowadays, most of the waste have been actually pushed into the sea. What I've seen in India. So will it not react with other minerals or other components which are being pushed into the sea?
What, can you repeat the question, please?
So what is happening? What I'm saying that most of the waste which has been generated from industries are pushed into the sea basically. After wastewater treatment and other processes. So this carbon dioxide, it's been injected into the level of seas as a sediment. So is it not possibility to get it reacted with other components?
No, no. So, as I said, this is a CO2 molecule which may react with the salt that are present in the sea. And as I said, like we are doing it in the seabed. It's not that into the water. So we're putting it below the ground, below the seabed, and where the CO2 may over a period of time get mineralized. Some of these studies are being reported in the literature, but more research is required. That what will happen, what will be the fate of the CO2 in the long run. But they will not react with otherwise some of these materials that you are talking about, because of course we do not want to even pollute the sea. All right. So here the CO2 is to be injected below the seabed.
Other materials are also not injected. Like I've seen that so near Bruges, a lot of waste are being generated, a lot of pollution is there. So most of even the sulfuric acid they are pushing it into sea only after wastewater treatment.
That we should not do. That should not be done. That's what. So nowadays there are various environmental regulations even to avoid some of this dumping of chemicals into the sea, because of course they may affect the local environment over there. So that
Right.
is of course discouraged.
So is there any process to monitor these industries, because you must have heard recently that most of the industries has been shut down because of pollution and, violations. So is it some system is there which keeps on monitoring these industries and the level of CO2 sulfuric acid they are emitting, and the government actually
Pollution.
gets an alarm?
So we have a state level pollution control board, we have central level pollution control board. So there are mechanisms that they should do the audit of overall some of these systems. Now, for example, I am working with one textile industry in Tirupur and in Tamil Nadu, and they actually used to generate lot of wastewater from the textile mill. And earlier they used to dump it into the river over there, and then because of this zero liquid discharge (ZLD) that come into effect, government said that you do not dump it that into the rivers. And therefore they have come up with a technology which now recycles most of these waters that they use for their applications, right? So there are mechanisms and technologies that are available. Only thing is that we have to adopt that, and this technology should be economical and sustainable.
Right. That's
Uh,
true.
Anybody else wants to ask any questions? Any participants? Participants, you can directly interact with the speaker.